We are going to talk about altitudes of the triangle today. Now, altitudes, this becomes, not just for this section, but this becomes a critical component for all shapes beyond triangles. So understanding what an altitude is going to be very important. All of our area and volume formulas that we're going to talk about in chapters 10, 11, 12, they all require us to be able to look at whatever shape we're finding the area, volume, surface area of, and identify altitudes and do that successfully, because obviously the formulas then rely on that value. Okay, so an altitude is a very important topic. So this is going to be talking about an altitude of a triangle, but it is found the same way, or is described the same way, defined the same way for other shapes as well. So the altitude of a triangle is the perpendicular segment from a vertex of the triangle to the line containing the opposite side. Okay? In other shapes, that formula or that definition might change to that it's the perpendicular segment from like one parallel side to another parallel side. We're talking about a parallelogram, or from a vertex to a particular side. Okay, maybe not necessarily the opposite side. So that's what we're talking about. Altitudes, specifically for a triangle, starts with a vertex and goes to the line containing the opposite side. And that's a key phrase there that says the line containing the opposite side. Why don't they just say to the opposite side? Why do they have to add this here? Okay, and hopefully I will have a demonstration here for you that explains this. Okay, but that highlighted phrase there is extremely important for the way we view and define an altitude. So an altitude of a triangle can be inside the triangle, or it can be outside the triangle. And when it's outside the triangle, that is why, and you're going to see it here in an image later, that is why that green highlighted statement needs to be added in our definition. But the altitude can be on the inside, it can be on the outside, or it can actually be one of the segments of your triangle, okay, if it's a right triangle. Yes.
Is it like whatever we did the other day? Like the right angle that's on the side of like the cube?
Yeah, so we're going to look at, so every altitude has every triangle has three altitudes, and they're going to have a point of concurrency. And that point can show up in different locations, and sometimes it does show up on the face. It's going to be at a different point, different position than what the circumcenter showed up on, but it does show up sometimes on the triangle. Got a question?
This has nothing to do with what we're talking about. What is that on the side of your thing?
Somebody drew that. I don't know what it is. The person that drew that, though, sits in your chair. That's weird. Okay. I didn't know she taped it there. All right, so an altitude of a triangle can be on the inside, can be on the outside, or it can be on the triangle. So one thing about that last bullet is if I find an altitude and it is on my triangle, that tells me I've got a right triangle. Or if I have a right triangle, I automatically know two of my altitudes. Okay, and the idea is, think about why that's got to be the case. If by definition, an altitude is the perpendicular segment from a vertex to of the triangle to the opposite side. Well, think about a right triangle. If that's my right angle, okay, and I start at this top vertex, how do I go perpendicular to the other side, the opposite side? So this would be the opposite side right here, correct? How do I go perpendicular to it? I have to follow that line right there, right?
Don't you have to go to the midpoint?
No, not for an altitude. For a median you do, but not for an altitude. I just need to be perpendicular to the opposite side. So that altitude followed the leg of the right triangle. If I wanted to go from this vertex perpendicular to the opposite side, so now here would be the opposite side of that vertex, To get there perpendicularly, if that's a word, then we have to follow that segment. So you see in both situations, in a right triangle, two of my altitudes are the legs of that triangle. Now, if I wanted to go from this vertex, so the right angle, I want to go from the right angle perpendicular to the opposite side, so there would be a third altitude. Does that kind of make sense, everybody? And that's just it's a unique situation because of that kind of a double feature here, where we got the legs of the right triangle are altitudes of the right triangle. So what I'd like to do is just kind of explain this visually a little bit better with these instead of the static pictures that we often get in textbooks and PowerPoints and that kind of stuff. So open that one up and then open this one up.
Are you hot?
Yes. Let's sound that.
All right, so in this image here, I'm going to, I don't know why, I can't remember why I made it this way. I don't need those, so let me hide them. Okay. We've got, you guys know what tangrams are? Tanagrams?
No. What's a telegram?
Ever seen those things before?
No.
You guys never went through like first grade, second grade, third grade, fourth grade, fifth grade, sixth grade, seventh grade? Those are like every elementary, middle school classroom. You've never seen those before?
In elementary, I don't know.
Okay. So these are like, there's like little wooden blocks that are cut out to be triangles, right? Some of them are parallelograms, some of them are rhombuses, some of them are, or whatever, okay? I remember talking about this in Mr. Miller's class when he introduced us to, you guys ever heard of MC Escher?
No. That's what I was about to say.
Have you ever seen these pictures, these paintings?
Oh, yeah, those are.
Okay, so Escher, like some of his are like optical illusion type. Not really optical illusion, but like you can see like inside, like the negative space, you've got the same shape that you have in the non-negative space. Those types of pictures. So that's MC Escher. So he like introduced us to tangrams and MC Escher this way. So this one's like one of his most famous ones.
You got taught by Mr. Moon?
Yeah.
I feel like we have like the same age.
No, he's got kids that have graduated college. Say again? 36.
Hurry.
I was thinking like 20.
Does that give me an
I thought you were at least 30, almost 40.
Well, 36 is.
That's not almost, I mean, you don't have any time
All right.
years.
So what I want to show you here with this is we start with any one of those triangles. Doesn't matter which one, because they're all the same triangle. So the way I want you to visualize this is that we have one of those wooden tangrams on our desk, and I ask you to set it up on your desk. So like that black line on the GeoGebra that I just put in there is your like desktop. Can you see that you could put, like if you had the actual wooden triangle in your hand, you could put it, rest it on your tabletop 3 different ways? That kind of makes sense?
No.
Okay.
When did
Well, let me see if I.
I've never talked about the square thing.
I got the same.
Yeah. I told you, today's not great. I'm tired.
I'm not gonna
No, I'm gonna stand up.
Think about it.
I don't know. I don't believe better than I did because I only used to watch.
Yeah, you gotta get it snap.
I don't have Snapchat.
What about Ferrari? I'm daddy's.
A stockbroker, the boringest thing, what's the word for it? Boring? Same thing.
Yep, I hear everything you guys say.
It is the most boring.
Everything?
A stockbroker, you literally go online and just,
Alright,
Alright, so, got my triangle here, right? So if my desktop is that black line, could I set my triangle up like this?
Sure.
Could I set it up like this?
Yeah.
Okay, could I set it up like that? Okay, so is the height, if I set it up like this, is this height right there? From there, straight down. How do I measure from a point to a line? What kind of lines do I use?
Straight line?
That's redundant. Aren't all lines by definition straight?
Yeah.
Perpendicular. Okay, so I'm gonna go from here, perpendicular down to the desktop, and that's gonna give me the height of that triangle. Does that make sense? Well, by definition, if I go from a point perpendicular to the opposite side, that's an altitude, right? So height, synonymous with altitude. Does that make sense? Okay. Now, if you measure that height, if we took a ruler and measured that, and then looked at the triangle this way, would you measure the altitude now or the height of this triangle from that vertex that is off the desk, perpendicular down to the desk? So that would be a different altitude. Does that make sense? Would it be a different height? Is that triangle shorter in that orientation than it is in that?
yes.
Yeah, okay? And that's what I'm trying to show you up there. So my desktop can take this triangle, and we can manipulate this triangle whatever I want it to look like. I can put my triangle so that CE is resting on the desktop, and then to measure the distance, let's make it an acute triangle first, so that they're all these altitudes on the inside. So I can measure straight down, and I can get that distance DF, and that would be an altitude, okay? And if I look at that distance from D to F, it's 4.86, okay? Now I can rotate my triangle, so now what is resting on the desk would actually have been this side here in the red triangle. Does that make sense? And that puts point C up in the air. And if I measure straight down, perpendicular to my desk, C prime to G would be 4.49, okay? Those two altitudes are different lengths, right? Okay. Now, the next one, if I look at, so now D prime, C prime, so it's actually this segment in the first triangle is now resting on my desk, and I could have that altitude, okay? So those are three different altitudes, and they could be kind of analyzed or described as three different heights, right? But what I want us to make sure we understand is that when we have a triangle just in general, okay, you see those I want to get rid of this, show, I want to go through. Well, I can't get rid of that purple color. Maybe I can make it white. Yeah, close enough. If we look at just the triangle at once and put all three altitudes in them simultaneously, okay? Instead of one at a time and rotating like we did in the last applet, you can see that all of these dotted lines from C to D, from A to F, and from B to E, those are altitudes, right? Okay, so if I, let's cover one of these up real quick. So that one, so let's make that, let's get rid of that one, and we'll get rid of that one. Just bear with me. There we go. All right. So if the only one that's left, the only altitude that's left is that red one. Would any of you think, I'm gonna call that H for that triangle, the way it's positioned? Would you call that the height of that triangle?
No.
No. Most people are gonna call C to D the height, right?
Yeah.
But that dotted line, that red dotted line, we can use as H for our altitude, okay? What's the area formula for a triangle?
Base times height times width.
Okay, so one of, I'm not gonna say it's the only, but one of the most common formulas for finding the area of a triangle is 1/2 base times height, okay? When we look at this situation here, so all I want to do is see if we can use GeoGebra to help us figure out what the area of this red triangle is. So if I've told you that this red triangle and this blue triangle and this green triangle, they're the same triangle, right? I've just rotated them.
Yeah.
So I should be able to say that area of the red one should be equal to 1/2 B times H. So in this case, 1/2 B, base is going to be this distance C to E. Does that make sense, everybody? So I'll ask it to calculate that here in a moment. So I'll take CE's length, and then I'll multiply that by DF's length, right? And DF's length in this case is 4.86. So if I do that, that should give me the area of that triangle. So let's go equals 1/2 C to E times then D to F. And when I do that, it gives me 15.38. It's that number right there. 15.38 is the area of that red triangle. .38. And this number here was 4.86. And I don't have CE's length yet, but we should be able to find it pretty easily. CE's length, 6.33. Okay, so we took those numbers and we multiplied those together, multiplied it by 1/2, and you got 15.38. And that's the area of that red triangle. Okay, now if I do the same thing for the blue one, okay, so the area of the blue one is going to be, again, 1/2 B times H. So 1/2, in this case, okay, B is going to be this distance right here, right? That's my base. Okay. The base is identified in this formula as the side that your altitude is perpendicular to. So calling that D to E. So let me see. D to E. And then H, in this case, would be C prime to G. So what we're doing is we're multiplying 1/2. DE, I'll ask it what it is here in a minute, times then C prime to G, which is 4.49. Let's see what it tells me that this distance here is, 6.86. Now, here's my question. Would you guys agree that these two numbers right here, 6.33 and 4.86, those are different than these numbers right here of 6.86 and 4.49?
Yeah.
Okay, they're different, but let's go ahead and see, what do I get in that blue triangle if I take 1/2 times the base times the height? So C prime to G. And you see right here that it gave 15.38 again. Okay, but I used completely different values to make a product for that area. Does that make sense? But what happened if you compare these? So what DF and C prime G. So this one was 4.86. So coming down here, didn't it decrease to 4.49?
Yeah.
So then to keep the products the same, this number here must have had to have increased down here. And they do that proportionally. Does that make sense? Okay. If we went into the green one, that would be completely different values. Okay, 6.05 and then that number there. So if I take 1/2 times, now it's E double prime times H, or E to H, and then D prime C double prime. If I multiply those together, what happened? E, oh, I do it right? I think let's see here. So E to that point right there is H. So E to H. And then let's go 1/2. And then E double prime H times D prime C double prime. I don't know why it's doing that, but let's see here. It should be, so E, so I'll just use the specific values. It's going to be a little bit off, but 1/2 times 6.05 times 5.08, if I do that, is that 15.37, pretty close to the 15.38? And these were 15.38 because I was using the exact values that were found through distance, and this one is 15.37 because these are off a little bit, I rounded them. I don't know why it's giving me, I'll look into that later. But we find the three areas of that triangle are exactly the same, but using different bases and different heights, right? Does that make sense to everybody? And that is an issue that people struggle with throughout this course because what have you always seen? What kind of triangle is the most common triangle that you've ever found the area for? A right triangle. And in a right triangle, if we've got this distance here and that distance there, let's say this is 3 and let's say that's 4, and you are asked to find the area, most of you just say, well, it's 1/2, 3 times 4, right? And the reason for that is because 3 is an altitude. But it could have also been, 1/2, 4 times 3 that way because of the commutative property of multiplication. But this is also an altitude, right? And what you've learned in the past, mainly because of the triangle that you've worked with the most, is that you just take the legs and multiply them together. Well, that's because one of the legs, if I view it as an altitude, the other leg is the base. Or if I view one leg as a base, then the other one is the altitude. Does that make sense? But you could also, does anybody know what this segment here's length is going to be?
7.
Not 7. What's Pythagoras says 3 squared plus 4 squared should equal this squared, right? So this actually ends up being 5. Okay? Then we could use that segment right there as H and this as the base and multiply 1/2 times that H times that base and still get the same area of 6 that we get here. Does that make sense, everybody? So I want to convince you of that real quick here. Let's say we've got that point. So we'll go down 1, 2, 3, and then we'll go 1, 2, 3, 4. So we get this triangle. Okay, and when we have that triangle, it should show me the area right there is 6, all the way at the bottom. Okay, which we would have gotten by taking 1/2 times 3 times 4, or 1/2 times 4 times 3. But now if I ask to find out what is, and it's a little bit difficult in regards to using GeoGebra to do this, Find that. That's the perpendicular line. That line right there is an altitude. But in regards to finding the area of my triangle, I'm only interested in really that segment right there, P to R. Okay? So if I take PR's length, it is 2.4. That is 5. Okay? If I take area equals 1/2, in this case, 2.4 times 5, does that still give me, where's the number at? What's going on here? Huh? I did? Oh, thank you. Still give me 6, right? Does that make sense? Okay. So you've been trained pretty much your entire life so far working with right triangles. Just multiply the legs together, multiply by half, and that gives you your area. But you don't have to. You could use that altitude there. Because if I take that triangle right there, and let's say we're going to, let's rotate this thing. Let's take this triangle, rotate around Q. Let's go A. Let's go, there's so many letters, U. Let's go S. Do it this way. Would it be okay to be able to take that triangle and maybe put it on my desk like that? Now would you guys, so this segment here is this black segment. Would this make more sense that that's the altitude to you or the height? That kind of makes sense? But you don't have to view it that way. You can have it on your desk flat and you've got 3 choices for H, you got 3 choices for B. We just have to make sure that we can justify those things. Is that okay with everybody? So when we look at a triangle, like I said, there's always going to be three altitudes. Okay, so this is a acute triangle, and that point of concurrency is referred to as the orthocenter. Okay, ortho. A lot of you people have anybody have braces? Have them. Who put your braces on? The orthodontist. Anybody ever go to have bone surgery or anything? What is that doctor called? An orthopedic surgeon, right? Okay. What's the prefix of ortho? Okay. Think about what your dentist does to your orthodontist does to your teeth. Makes them what? Straight compared to what? Okay, so they take your palate, essentially your gums, right? And don't they try to make your teeth perpendicular to them? Does that make sense? Orthopedic surgeon, okay? Ultimately, their goal is to keep you upright, to keep you perpendicular to the ground, right? If I punch over, I got back problems, they're going to try to straighten me out, right? Okay, so now I'm perpendicular to the ground. Anything that starts with the prefix of ortho has something to do with being perpendicular. Okay, another word for it, and it's usually we use it in reference to making lines perpendicular to planes. So think about your teeth when you go to the orthodontist, the gaps in your teeth or the like the seams between two teeth. They're trying to keep those all perpendicular to the roof of your mouth, or the plane that your gums create. So usually, the word orthogonal talks about taking a line and making it perpendicular to a plane. Does that make sense? So if, let me see my yardstick where I put that thing. There it is. So right now, if I take my yardstick and just like hold it like this, it is not perpendicular to the ceiling, right? Okay? But maybe now it is, right? So instead of saying it's perpendicular to the ceiling, the way we say this is that this yardstick is orthogonal to the ceiling. Okay? But the word ortho for us just means perpendicular. So the reason I say that is because hopefully we are going to be able to keep track of what creates the circumcenter, what creates the centroid, what creates the incenter, what creates the orthocenter. There's 4 points we've talked about so far, and they're all created by different lines, right? If I want to remember what the orthocenter is, I remember altitudes, because altitudes are perpendicular and ortho means perpendicular. Okay? Now you might say, well, perpendicular bisectors that create the circumcenter is the same thing. And yeah, you were right. So you'll have to be able to distinguish those two. Okay? But at least gives you maybe a way of differentiating between the incenter and the centroid. Okay? So the orthocenter is created by the altitudes. Okay, now your orthocenter, think about this. This is an acute triangle. So the orthocenter is on the inside of your triangle, right? Okay. If that's the intersection of perpendicular segments, okay, from one point perpendicular to the opposite side, where does your orthocenter going to be in that triangle?
The right angle.
Okay, so in a right triangle, your orthocenter is the right angle. Okay, so Math Excel might present a question. It might give you 3 points and say find the orthocenter. And as you graph those 3 points, you might find out, hey, 2 of these points are vertical, 2 of these points are horizontal to one another. So that means that there must be a right angle there, right? When they come together, from one of the vertices is a right angle. And they ask you, well, where's the orthocenter? Well, it's got to be at that point that was the right angle. Does that make sense? So if I were to give you in Math Excel these points, B, where are they at? These 3 points right there. Because 2 of them have x values of 4, and because 2 of them have y values of 14, we know automatically that 2 of them are horizontal, 2 of them are vertical. And then that tells us automatically when we look at these that point A is the right angle. And if A is the right angle, then that's the location. That's what I would type in for the orthocenter. Okay? So in an acute triangle, orthocenter is on the inside. Right triangle, orthocenter is on the triangle. Where is the orthocenter in an obtuse triangle? On the outside. Okay? So what you have to do, so right now what I'm showing you, right, this demonstration does not, I think if I unhighlight that box, I've made this so long ago. Yeah, okay. So this segment right there is an altitude, okay? And if I was going to use h, okay, lowercase h for like a formula for area of a triangle, that's the distance that I would use. However, that is really the entire altitude. Does that make sense? Okay. And this here is the entire second or third altitude. Do they all intersect down here at a point of concurrency? And that's the orthocenter down there outside the triangle. That is the reason why, that triangle right there is the reason why in our definition we had to say that the perpendicular segment from a vertex of the triangle to the line containing the opposite side. That idea that we have to have to the line containing the opposite side is for this purpose right here. If I have a triangle that is obtuse, Okay? Every obtuse triangle, 2 of your altitudes are going to be on the outside. Because if I'm going to ask, if you start at C and you want to go perpendicular to the opposite side, if I just leave it as being able to go to the opposite side, I could only have my altitude would have to be one of these black segments, right? Are any of those black segments going to be perpendicular to the segment between A and B? No. The only way they're going to be perpendicular is if I put down there, right? So what do I have to do then is I have to extend the side that contains the line that contains the opposite side to actually find that altitude. Is that okay with everyone? And if I do that with that one, then I'm going to have to do that same thing. I'll have to extend this line here, and maybe the altitude, I don't know, I can turn my head a little bit, maybe the altitude's like that. All right? Do we understand altitudes for triangles? Okay. Acute, the orthocenter is on the inside. Right, it's on the right angle. And obtuse, it's on the outside. All right, we'll stop there for today, folks. They took your computers.